The universe is not a silent void. It's a stage alive with motion, where planets, stars, and galaxies move in a breathtaking choreography dictated by gravity. Every orbit, every collision, every cosmic event is part of a grand performance, a gravitational ballet that has been unfolding for billions of years. But what exactly keeps these celestial dancers in sync? How does gravity, an invisible force, orchestrate such a vast and intricate cosmic dance? In this video, we'll uncover the secrets of celestial dynamics, the science that reveals how gravity shapes the universe. From the birth of solar systems to the dramatic collisions of galaxies, we'll explore how this fundamental force not only governs the cosmos, but also holds the key to understanding our place within it. So, let's step into this cosmic theater and witness the gravitational ballet that defines the very fabric of existence. The story of celestial dynamics begins in the early 17th century, when humanity first began to unravel the mathematical secrets of the heavens. Johannes Kepler, a German astronomer, gazed at the night sky and saw more than just scattered stars. He saw patterns. Through meticulous observations and calculations, Kepler discovered that planets don't move in perfect circles, as once thought, but in elliptical orbits around the Sun. This was his first law of planetary motion, a revelation that shattered centuries of belief in perfectly circular celestial paths. But Kepler didn't stop there. He went on to describe how planets speed up as they approach the Sun and slow down as they move away, a rhythm governed by what he called the harmony of the spheres. These laws were the first steps in decoding the choreography of the cosmos. Then came Isaac Newton, a towering figure in science, who took Kepler's work and transformed it into something even more profound. Newton asked a simple yet revolutionary question: what keeps the planets in their orbits? The answer was gravity, a force that not only pulls an apple to the ground, but also binds the moon to the Earth and the Earth to the Sun. Newton's law of universal gravitation revealed that every object in the universe attracts every other object with a force proportional to its mass and inversely proportional to the square of the distance between them. Suddenly, the motion of celestial bodies wasn't just a mysterious dance. It was a predictable, calculable interaction governed by a universal force. Together, Kepler and Newton didn't just explain the movements of planets, they gave us a new lens through which to view the cosmos. Kepler's laws provided the how, and Newton's gravity explained the why. Their work didn't just describe the universe, it allowed us to predict its behavior. This partnership of observation and theory laid the groundwork for modern astrophysics, transforming celestial dynamics from a philosophical pursuit into a rigorous science. It's thanks to their discoveries that we can now explore the gravitational ballet of galaxies, black holes, and even the expansion of the universe itself. Their legacy is a testament to the power of human curiosity and the enduring quest to understand the forces that shape our existence. Gravity is the invisible maestro of the cosmos, conducting the movements of celestial bodies with precision and grace. It's the force that keeps Earth circling the Sun, the Moon tethered to our planet, and even entire galaxies swirling in vast, intricate patterns. But what exactly is this force, and how does it wield such immense power over the universe? At its core, gravity is the pull between masses, a fundamental interaction that shapes everything from the smallest asteroid to the largest supercluster of galaxies. Think of it as an unseen thread that connects all objects in space. No matter how distant, the more massive an object, the stronger its gravitational pull. That's why the Sun, with its enormous mass, holds the planets in its sway, guiding them along their elliptical orbits. But gravity doesn't just keep celestial bodies in line, it also plays a crucial role in their creation. Stars, for example, are born from vast clouds of gas and dust that collapse under their own gravitational pull. Over time, these clouds condense, heat up, and ignite, giving birth to the fiery furnaces that light up the universe. Similarly, galaxies form when gravity pulls together countless stars, gas clouds, and dark matter, weaving them into the majestic spirals and glowing clusters we observe today. For centuries, Newton's law of universal gravitation was the definitive explanation for this force. But in the early 20th century, Albert Einstein revolutionized our understanding with his theory of general relativity. According to Einstein, gravity isn't just a force, it's the result of spacetime itself being warped by mass and energy. Picture a bowling ball placed on a trampoline, creating a deep well that causes smaller objects to roll toward it. In the same way, massive objects like stars and planets curve the fabric of spacetime, and this curvature dictates the paths that other objects follow. This new perspective didn't just refine our understanding of gravity, it transformed it. General relativity explained phenomena that Newton's laws couldn't, such as the bending of light around massive objects, known as gravitational lensing, or the precise orbit of Mercury around the Sun. It also laid the groundwork for our modern understanding of black holes, where gravity is so intense that not even light can escape. By exploring gravity, we uncover the hidden mechanisms that orchestrate the universe's grandest performances. It's not just a force, it's the architect of cosmic order, shaping the birth, life, and death of stars and galaxies. And as we delve deeper into its mysteries, we gain a profound appreciation for the delicate balance that allows the gravitational ballet to unfold across the vast expanse of space and time. Our solar system is a gravitational playground, a dynamic stage where the sun's immense gravity takes center stage, shaping the movements of planets, moons, and countless other celestial objects. Picture the sun as the conductor of an orchestra, its gravitational pull guiding the planets in their orbits like musicians following a precise score. Each planet, from speedy Mercury to distant Neptune, dances to the rhythm of this cosmic symphony, held in place by the delicate balance of gravity and motion. At the heart of this system lies the Sun, a star so massive that its gravity dominates everything within its reach. The planets orbit the Sun in elliptical paths, each one tracing a unique trajectory determined by its speed and distance. This balance between the Sun's gravitational pull and a planet's forward motion, what scientists call centripetal force, keeps the planets from spiraling into the Sun or flying off into the void. It's a cosmic tug of war, perfectly calibrated over billions of years, but the solar system isn't just about the Sun and the planets. Moons, asteroids, and comets also play their parts in this gravitational dance. Take Earth's moon, for example. It's not just a passive companion, it's locked in a gravitational embrace with our planet, creating the tides and stabilizing Earth's axial tilt. Even smaller objects, like the asteroids in the asteroid belt, are influenced by the Sun's gravity, their paths shaped by the interplay of forces from nearby planets like Jupiter. One of the most fascinating phenomena in the solar system is orbital resonance, a kind of gravitational harmony between celestial bodies. Imagine two objects locked in a rhythmic pattern, where their orbits align in a precise ratio. For instance, Jupiter's moons Io, Europa, and Ganymede are in a 1-2-4 resonance, meaning for every orbit Ganymede completes, Europa completes 2, and Io completes 4. This delicate balance isn't just a cosmic coincidence, it's a testament to the intricate choreography of gravity. Then there are Lagrange points, special spots in space where the gravitational forces of two large bodies, like the Sun and a planet, create zones of equilibrium. Objects placed at these points can remain relatively stable, as if caught in a gravitational sweet spot. Space agencies have even used Lagrange points to position satellites and telescopes, like the James Webb Space Telescope, which orbits the Sun at a Lagrange point to maintain a steady view of the cosmos. The solar system is more than just a collection of planets and moons. It's a microcosm of the universe, offering a glimpse into the fundamental principles of celestial dynamics. By studying how gravity shapes the orbits and interactions of these objects, we gain insights into the forces that govern galaxies, star systems, and even the universe itself. It's a reminder that the same laws that keep Earth in its orbit also shape the grandest structures in the cosmos, connecting us to the vast, intricate dance of the universe. Orbital mechanics is the hidden language of the cosmos, a precise science that reveals how objects move through the vast expanse of space under the influence of gravity. At its core, it's the study of motion, how celestial bodies and human-made spacecraft alike navigate the intricate web of gravitational forces that shape their paths. To truly grasp this science, we need to explore the fundamental principles that govern these movements, from the speed of an object to the delicate balance of forces that keep it in orbit. Let's start with velocity, the speed and direction of an object's motion. In space, velocity is everything. If an object moves too slowly, gravity will pull it back toward the larger body it's orbiting. Move too fast, and it might break free entirely, escaping the gravitational grip. The perfect balance between these extremes is what creates a stable orbit. For example, the International Space Station orbits Earth at a staggering speed of roughly 28,000 kilometers per hour, fast enough to counteract Earth's gravity, but not so fast that it flies off into space. This delicate equilibrium is the foundation of orbital mechanics, but velocity alone doesn't tell the whole story. Acceleration, the change in velocity over time, plays a crucial role in how objects move through space. When a spacecraft fires its engines, it accelerates, altering its trajectory. This principle is essential for missions like the Apollo program, where astronauts had to precisely adjust their speed and direction to leave Earth's orbit, travel to the Moon, and return safely. Without a deep understanding of acceleration, such feats of space exploration would be impossible. One of the most fascinating concepts in orbital mechanics is escape velocity, the speed required for an object to break free from a planet or star's gravitational pull. For Earth, that speed is about 11.2 kilometers per second. Achieving escape velocity is what allows spacecraft like Voyager 1 and 2 to leave our solar system entirely, venturing into the interstellar void. It's a reminder that gravity, while invisible, is a force that must be reckoned with, and overcoming it requires both precision and power. Spacecraft don't just rely on brute force to navigate the solar system, though. They use clever techniques like gravity assists, also known as slingshot maneuvers, to gain speed and efficiency. By flying close to a planet, a spacecraft can borrow some of the planet's orbital energy, using its gravity to slingshot forward. This technique has been used in countless missions, from the Galileo probe exploring Jupiter to the New Horizons spacecraft speeding toward Pluto. It's a brilliant example of how orbital mechanics turns gravity from a challenge into a tool. Another key concept is the Hohmann transfer orbit, an energy-efficient path used to move a spacecraft from one orbit to another. Imagine wanting to travel from Earth to Mars. Instead of launching straight toward the red planet, a spacecraft follows an elliptical orbit that intersects both Earth's and Mars's paths at just the right moments. This method minimizes fuel consumption, making long-distance space travel more feasible. It's a testament to the ingenuity of orbital mechanics, turning the complexities of gravity into a roadmap for exploration. Understanding orbital mechanics isn't just about solving equations or calculating trajectories. It's about unlocking the secrets of the universe, revealing how gravity shapes the paths of planets, moons, and even the spacecraft we send to explore them. From the precise dance of celestial bodies to the daring maneuvers of human-made probes, orbital mechanics is the science that connects us to the cosmos, showing us how to navigate the vast, gravitational ballet of the universe. Johannes Kepler's 3 laws of planetary motion are like the sheet music for the gravitational ballet, a set of rules that reveal how celestial bodies move in harmony. These laws, discovered in the early 17th century, didn't just describe the motion of planets, they fundamentally changed how we perceive the universe. Let's break them down, one by one, to uncover the elegance and precision behind the cosmic dance. The first law, often called the law of ellipses, tells us that planets orbit the Sun not in perfect circles, as once believed, but along elliptical paths. Imagine a stretched-out circle, with the Sun positioned at one of the 2 focal points. This means a planet's distance from the Sun isn't constant. It varies as it travels along its orbit. When the planet is closer to the Sun, it's at perihelion. When it's farthest away, it's at aphelion. This discovery was revolutionary because it shattered the ancient belief in perfectly circular celestial motion, showing that the universe operates with a subtle, natural asymmetry. Kepler's second law, the law of equal areas, reveals how planets move faster when they're closer to the Sun and slower when they're farther away. Picture a planet sweeping out an area in space as it orbits. According to this law, the planet covers equal areas in equal amounts of time, no matter where it is in its orbit. Imagine a comet racing through its closest approach to the Sun, then gradually slowing as it moves away. This speeding up and slowing down isn't random. It's a precise, predictable rhythm dictated by gravity. It's as if each planet knows exactly how to adjust its pace to maintain the cosmic balance. The third law, the law of harmonies, connects a planet's orbital period, the time it takes to complete one orbit, to its average distance from the Sun. Specifically, the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This might sound complex, but it means there's a mathematical relationship between how far a planet is from the Sun and how long its year lasts. For example, Mercury, the closest planet to the Sun, zips around in just 88 Earth days, while distant Neptune takes over 165 Earth years to complete its orbit. This law doesn't just apply to planets. It works for moons, comets, and even artificial satellites, offering a universal formula for understanding orbital motion. Kepler's laws aren't just abstract principles. They're tools that allow us to predict and understand the movements of celestial bodies. They explain why comets like Halley's Comet return to our skies at predictable intervals, and why moons like Europa and Io orbit Jupiter in such precise patterns. These laws also laid the groundwork for Newton's theory of gravity, bridging the gap between observation and explanation. But Kepler's legacy goes beyond equations and predictions. His laws remind us that the universe operates with a kind of mathematical beauty, a hidden order that we can uncover through curiosity and observation. They show us that the gravitational ballet isn't chaotic. It's a meticulously choreographed performance, with each celestial body following its own unique rhythm. And as we continue to explore the cosmos, from the orbits of distant exoplanets to the intricate dance of binary stars, Kepler's laws remain our guide, helping us decode the mysteries of the universe one orbit at a time. Isaac Newton's law of universal gravitation wasn't just a scientific breakthrough, it was a revelation that reshaped our understanding of the cosmos. Picture this, a young Newton sitting beneath an apple tree, pondering the forces of nature, when suddenly an apple falls to the ground. This simple observation sparked a profound question. If gravity pulls an apple toward Earth, could it also pull the moon toward Earth, keeping it in orbit? That question led to one of the most groundbreaking discoveries in human history, a universal law that applies not just to apples and moons, but to every object in the universe. At its heart, Newton's law of universal gravitation states that every particle of matter attracts every other particle with a force that depends on two things: their masses and the distance between them. The equation itself is elegant in its simplicity. The force of gravity is proportional to the product of the two masses and inversely proportional to the square of the distance separating them. In other words, the more massive the objects and the closer they are, the stronger the gravitational pull between them. This law didn't just explain why apples fall, it revealed why planets orbit the sun, why moons circle planets, and why galaxies hold together across unimaginable distances. Newton's law was a game changer because it brought predictability to the cosmos. Before his work, the movements of celestial bodies seemed mysterious and chaotic. But with this equation, scientists could calculate the gravitational force between any two objects, whether it was the Earth and the Moon or two distant stars. Suddenly, the universe wasn't just a collection of random motions, it was a system governed by precise, mathematical rules. This was the moment when celestial dynamics truly became a science, allowing us to predict eclipses, comets, and even the existence of undiscovered planets. But while Newton's law was revolutionary, it wasn't perfect. It worked brilliantly for most scenarios, but there were a few puzzles it couldn't solve. Take Mercury, for example. Its orbit around the Sun doesn't quite match Newton's predictions, it shifts slightly over time, a phenomenon known as the precession of Mercury's perihelion. For centuries, this tiny discrepancy puzzled astronomers. It wasn't until Albert Einstein introduced his theory of general relativity in the early 20th century that we finally had an explanation. Einstein showed that gravity isn't just a force between masses, it's the result of spacetime itself being curved by mass and energy. This new perspective not only solved the mystery of Mercury's orbit, but also opened the door to understanding black holes, gravitational waves, and the expansion of the universe. Despite its limitations, Newton's law of universal gravitation remains a cornerstone of physics. It's accurate enough to guide spacecraft to distant planets and to calculate the trajectories of comets. Even today, when we launch satellites or plan missions to Mars, we rely on Newton's equations. They're a testament to the power of human ingenuity, a set of principles that, while refined by later discoveries, still form the foundation of our understanding of the universe. Newton's work reminds us that science is a journey, not a destination. His law of universal gravitation was a monumental step forward, but it also set the stage for even greater discoveries. It's a story of curiosity, of asking questions, and of building on the work of those who came before. And as we continue to explore the cosmos, from the orbits of distant exoplanets to the behavior of galaxies, Newton's legacy lives on, a guiding light in our quest to understand the gravitational ballet that shapes the universe. Albert Einstein's theory of general relativity didn't just refine our understanding of gravity, it completely redefined it. While Newton's law of universal gravitation had served humanity well for centuries, it couldn't explain everything. Einstein's breakthrough came when he shifted the focus from gravity as a force to gravity as a consequence of the very fabric of the universe. According to general relativity, massive objects like stars and planets don't just exert a pull on other objects, they warp the spacetime around them, creating a kind of cosmic landscape that dictates how everything moves. Picture spacetime as a vast, stretchy sheet. When you place a heavy object like the sun on this sheet, it creates a deep well. Planets, moons, and even light follow the curves of this well, much like a marble rolling along the slopes of a bowl. This curvature isn't just a metaphor, it's a fundamental property of the universe. The more massive the object, the deeper the well, and the stronger its influence on nearby objects. This elegant idea not only explained the orbits of planets, but also opened the door to understanding some of the most extreme and mysterious phenomena in the cosmos. One of the most striking predictions of general relativity is gravitational lensing, a phenomenon where light from a distant object bends as it passes near a massive object, like a galaxy or a black hole. Imagine looking through a glass of water and seeing the world distorted around you. In the same way, massive objects in space act like cosmic lenses, bending and magnifying the light from objects behind them. This effect allows astronomers to see distant galaxies that would otherwise be too faint to detect, effectively turning massive objects into natural telescopes. Gravitational lensing isn't just a curiosity, it's a powerful tool for exploring the universe, helping us map dark matter and study the earliest moments of cosmic history. Then there are black holes, perhaps the most dramatic consequence of general relativity. These are regions of spacetime where gravity is so intense that nothing, not even light, can escape their pull. Black holes form when massive stars collapse under their own gravity, creating a point of infinite density called a singularity. Around this singularity lies the event horizon, the point of no return where the gravitational grip becomes inescapable. But black holes aren't just cosmic vacuum cleaners, they're laboratories for testing the limits of our understanding. They reveal the extreme nature of gravity, showing how it can warp time itself. Near a black hole, clocks tick slower, and the fabric of spacetime twists in ways that defy our everyday intuition. Einstein's theory also solved a long-standing mystery, the precession of Mercury's orbit. For centuries, astronomers had noticed that Mercury's elliptical path around the Sun shifts slightly over time, an effect that Newton's laws couldn't fully explain. General relativity accounted for this shift by describing how the Sun's mass curves spacetime, subtly altering Mercury's trajectory. This was one of the first major confirmations of Einstein's theory, proving that it wasn't just a mathematical curiosity, it was a true description of how the universe works. But general relativity isn't just about explaining the cosmos as we see it today. It also gives us a glimpse into the universe's origins. The theory predicts that spacetime itself can stretch and expand, a concept that laid the groundwork for the Big Bang theory. It also describes how massive objects can create ripples in spacetime, known as gravitational waves, which were first detected in 2015. These waves, caused by cataclysmic events like the collision of black holes, allow us to listen to the universe in a whole new way, opening a window into the most violent and energetic processes in existence. Einstein's general relativity transformed gravity from a simple force into a dynamic, geometric phenomenon. It showed us that the universe isn't just a collection of objects moving through space, it's a living, breathing entity where space and time are intertwined, shaped by the mass and energy within it. And as we continue to explore the cosmos, from the edges of black holes to the farthest reaches of the universe, Einstein's theory remains our most powerful tool for understanding the gravitational ballet that defines the very fabric of reality. Black holes are the universe's ultimate enigmas, regions where gravity becomes so overwhelming that it bends the rules of reality itself. Imagine a place where the pull is so intense that not even light, the fastest thing in the universe, can escape. These cosmic anomalies are not just theoretical curiosities, they're real, observable phenomena that challenge our understanding of space, time, and gravity itself. But how do they form, and what role do they play in the grand dance of celestial dynamics? The birth of a black hole often begins with the death of a star. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The star collapses in on itself, triggering a supernova explosion so powerful that it outshines an entire galaxy. What remains is a core so dense that its gravity becomes infinite, creating a black hole. This process, known as stellar collapse, is one of the most violent and awe-inspiring events in the cosmos. But black holes can also form through other means, such as the merging of neutron stars or the direct collapse of massive gas clouds in the early universe. Once formed, a black hole's influence extends far beyond its event horizon, the boundary beyond which nothing can escape. Its gravity warps spacetime so profoundly that it can bend light, slow time, and even trap matter in an endless spiral. Yet, despite their reputation as cosmic vacuum cleaners, black holes are not just destructive forces. They play a crucial role in shaping the universe around them. For instance, supermassive black holes, which can weigh billions of times more than our Sun, often reside at the centers of galaxies. Their immense gravity helps hold galaxies together, influencing the orbits of stars and gas clouds and driving the formation of new stars. In recent years, black holes have moved from the realm of theory to the forefront of observational astronomy. One of the most groundbreaking moments came in 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole. This remarkable achievement captured the silhouette of a supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of hot gas. The image wasn't just a scientific milestone, it was a visual confirmation of Einstein's predictions about how gravity warps light and spacetime. It also opened a new window into studying these mysterious objects, allowing us to probe their properties and test the limits of our understanding. Black holes also serve as cosmic laboratories, revealing the extreme behavior of gravity. For example, when two black holes collide, they create ripples in spacetime called gravitational waves. These waves, first detected in 2015, provide a new way to listen to the universe, offering insights into the nature of black holes and the fabric of spacetime itself. They've shown us that black holes can spin, merge, and even ring like bells, emitting gravitational waves that carry information about their mass, spin, and shape. Yet for all we've learned, black holes remain shrouded in mystery. What happens to matter that falls into a black hole? Do black holes ever die? And if so, what does that look like? These questions drive scientists to push the boundaries of physics, exploring concepts like Hawking radiation, quantum gravity, and the possibility of wormholes. Black holes are not just gravity's ultimate expression, they're also a reminder of how much we still have to discover about the universe. From their formation to their role in shaping galaxies, black holes are a testament to the power and complexity of celestial dynamics. They challenge us to rethink our understanding of gravity, spacetime, and the very nature of reality. And as we continue to study them, from their event horizons to the echoes of their collisions, we're not just unraveling the secrets of black holes, we're uncovering the deeper truths that govern the cosmos. Galaxies are the grand theaters of the cosmos, where stars, gas, and dark matter come together in a breathtaking performance orchestrated by gravity. Imagine a galaxy not as a static collection of stars, but as a dynamic, ever-changing system, where every object, from the tiniest speck of dust to the most luminous star, plays a role in the cosmic dance. This is the realm of galactic dynamics, the study of how gravity shapes the structure, motion, and evolution of galaxies over billions of years. At the heart of every galaxy lies a delicate balance between the gravitational pull of its mass and the motion of its stars. Take spiral galaxies, for instance, like our own Milky Way. These galaxies are characterized by their stunning, swirling arms, which seem to stretch out like the arms of a cosmic dancer. But how do these arms form and maintain their shape? The answer lies in a phenomenon called density waves. As stars and gas clouds move through the galaxy, they encounter regions of higher density, where gravity slows them down. This creates a ripple effect, compressing gas and triggering the birth of new stars. Over time, these waves give rise to the iconic spiral patterns we see, a testament to gravity's ability to sculpt beauty on a cosmic scale. Not all galaxies are spirals, though. Elliptical galaxies, for example, are shaped more like stretched-out spheres, with stars orbiting in all directions like a swarm of bees. These galaxies often form when two or more spiral galaxies collide, their stars and gas merging into a chaotic but gravitationally stable system. The result is a galaxy with little gas left to form new stars, its stellar population aging gracefully over billions of years. These collisions aren't just random events, they are part of the galaxy's life cycle, driven by the same gravitational forces that govern their existence. But there's a hidden player in this cosmic ballet, dark matter. Though invisible and undetectable by conventional means, dark matter makes up the majority of a galaxy's mass. Its gravitational influence is what keeps galaxies from flying apart, acting as an unseen scaffold that binds stars and gas together. Without dark matter, galaxies as we know them simply wouldn't exist. Its presence is most evident in the rotation curves of galaxies, the way stars orbit the galactic center. If galaxies were made only of visible matter, stars on the outer edges would move more slowly as gravity weakens with distance. But observations show that these stars move just as quickly as those closer to the center, a clear sign that something massive and invisible is holding them in place. Dark matter's role extends beyond individual galaxies. It also shapes the large-scale structure of the universe, forming a cosmic web that connects galaxies across vast distances. This web acts as a gravitational highway, guiding the formation of galaxy clusters and superclusters. In fact, the distribution of dark matter in the early universe played a crucial role in determining where galaxies would form, creating the intricate patterns we observe today. Galactic dynamics isn't just about understanding how galaxies move, it's about uncovering the forces that shape their past, present, and future. From the birth of stars in spiral arms to the collisions that transform galaxies, gravity is the constant thread weaving through the story. And as we peer deeper into the cosmos, studying the motions of stars and the distribution of dark matter, we gain a deeper appreciation for the universe's complexity. It's a reminder that even on the grandest scales, the dance of gravity continues, shaping the evolution of galaxies and the destiny of the cosmos itself. Dark matter is the unseen partner in the cosmic dance, a mysterious substance that makes up roughly 85% of the universe's total mass. Yet, despite its overwhelming presence, it remains invisible: no light, no heat, no detectable signals. So how do we know it's there? The story of dark matter begins not with what we can see, but with what we can't. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of galaxies millions of light years away. He noticed something strange. The galaxies were moving so fast that, based on the visible matter he could observe, they should have flown apart, but they didn't. Zwicky hypothesized that there must be some unseen mass holding the cluster together, which he called dark matter. At the time, his idea was met with skepticism. But decades later, another piece of evidence would bring dark matter into the spotlight. In the 1970s, astronomer Vera Rubin made a groundbreaking discovery while studying the rotation of spiral galaxies. She found that stars on the outer edges of galaxies were moving just as fast as those near the center, something that defied the laws of gravity as we understood them. If galaxies were made only of visible matter, the outer stars should have been moving more slowly. Rubin concluded that there had to be an invisible halo of dark matter surrounding each galaxy, exerting a gravitational pull that kept the stars in place. This discovery turned dark matter from a fringe idea into a cornerstone of modern astrophysics. But what exactly is dark matter? Scientists believe it's a type of particle that doesn't interact with light or ordinary matter, making it incredibly difficult to detect. It's not made of atoms, protons, or electrons. It's something entirely different. Yet, its gravitational effects are undeniable. For instance, dark matter's presence is revealed through gravitational lensing, a phenomenon where the gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. By studying these distortions, astronomers can map the distribution of dark matter, revealing vast, invisible structures that stretch across the universe. The search for dark matter is one of the most exciting challenges in science today. Experiments deep underground, like those using liquid xenon or cryogenic detectors, aim to catch a fleeting interaction between dark matter particles and ordinary matter. In space, telescopes like the Hubble and James Webb are searching for clues in the way galaxies move and cluster together. And at the Large Hadron Collider, physicists are smashing particles together, hoping to create dark matter in the lab. Dark matter isn't just a scientific curiosity, it's a key player in the gravitational ballet of the cosmos. It shapes the formation of galaxies, guides the evolution of the universe, and helps us understand the very fabric of reality. While we may not yet know what it is, the evidence for its existence is overwhelming. And as we continue to search for answers, dark matter reminds us that the universe is far more mysterious and wondrous than we ever imagined. If dark matter is the unseen hand that holds galaxies together, dark energy is the force pushing them apart, a mysterious influence driving the universe's accelerating expansion. Imagine the universe as a cosmic balloon, not just inflating but doing so faster and faster over time. This discovery, one of the most profound in modern cosmology, has reshaped our understanding of the cosmos and introduced a new player in the gravitational ballet, dark energy. The story of dark energy begins in the late 1990s, when astronomers studying distant supernova made a startling observation. These exploding stars, known as Type 1a supernova, serve as standard candles in space. Their brightness allows scientists to measure cosmic distances with precision. What researchers found was unexpected. The supernova were fainter than they should have been, meaning they were farther away than predicted. This could only mean one thing: the universe wasn't just expanding, it was doing so at an accelerating rate. The discovery was so revolutionary that it earned the researchers the Nobel Prize in Physics in 2011, forever changing our view of the cosmos. But what's causing this acceleration? That's where dark energy comes in. Scientists believe it's a form of energy permeating all of space, acting as a kind of anti-gravity that counteracts the pull of matter and dark matter. Unlike gravity, which draws objects together, dark energy pushes them apart, driving galaxies away from one another at ever-increasing speeds. The simplest explanation for dark energy is the cosmological constant, a term Albert Einstein introduced and later dismissed in his equations of general relativity. Einstein originally added it to describe a static universe, but when the universe was found to be expanding, he called it his biggest blunder. Ironically, it may now be the key to understanding the universe's accelerating expansion. The implications of dark energy are profound. If it continues to dominate the universe, the cosmos will keep expanding faster and faster, eventually pulling galaxies so far apart that they become invisible to one another. Over billions of years, this could lead to a big freeze, where the universe becomes a cold, dark, and lonely place, but that's just one possibility. Some theories suggest dark energy might evolve over time, potentially leading to a big rip, where even atoms are torn apart, or a big crunch, where the expansion reverses and the universe collapses back on itself. These scenarios remind us that the universe's fate is still an open question, one that dark energy holds the key to answering. Dark energy also plays a crucial role in shaping the large-scale structure of the universe. On cosmic scales, gravity and dark energy are locked in a tug-of-war. Gravity pulls matter together, forming galaxies and galaxy clusters, while dark energy pushes space apart, creating vast voids between them. This interplay gives the universe its cosmic web-like structure, with galaxies strung along filaments of dark matter, separated by immense, empty regions. It's a delicate balance, one that has shaped the universe's evolution and continues to guide its future. Yet, for all we've learned, dark energy remains one of the greatest mysteries in science. What is it made of? Does it change over time? And why does it have the exact value it does? These questions drive some of the most ambitious experiments in cosmology, from the Dark Energy Survey to the upcoming Euclid Space Telescope. By mapping the universe's expansion and studying the distribution of galaxies, scientists hope to uncover the secrets of dark energy and its role in the cosmos. Dark energy is more than just a scientific puzzle. It's a reminder of how much we still have to discover about the universe. It challenges us to rethink our understanding of gravity, space, and time, and pushes us to explore the deepest mysteries of existence. As we continue to study this enigmatic force, we're not just learning about the universe's past and future, we're uncovering the fundamental laws that govern reality itself. And in doing so, we're taking another step toward understanding the grand, gravitational ballet that shapes the cosmos. The universe is a sculptor, and gravity is its chisel. Every solar system begins as a vast, swirling cloud of gas and dust, a molecular cloud drifting through the cosmos. These clouds are the nurseries of stars and planets, and within them, gravity works its magic, transforming chaos into order. But how does this process unfold? How does a diffuse cloud of material give rise to something as intricate as a solar system? The story begins with a delicate balance, or rather, the breaking of it. When a molecular cloud becomes dense enough, gravity takes over. Imagine a small region within the cloud where particles are slightly closer together than elsewhere. This slight imbalance creates a gravitational pull, drawing in more material. As the region grows denser, its gravity strengthens, pulling in even more gas and dust. This runaway process, known as gravitational collapse, is the first step in the birth of a solar system. Over time, the collapsing cloud flattens into a spinning disk, with most of the material gathering at the center. Here, under immense pressure and heat, a star begins to form, a fiery core that will one day light up its planetary system. But the story doesn't end with the star. The material in the surrounding disk doesn't simply vanish. It becomes the building blocks for planets, moons, and other objects. Tiny particles of dust and ice collide and stick together, forming clumps called planetesimals. These clumps grow larger as they sweep up more material, eventually becoming protoplanets. Gravity plays a crucial role here, not just by pulling material together, but by shaping the orbits of these growing bodies. Over millions of years, the protoplanets collide and merge, creating the planets we know today. This process isn't random. It's governed by the laws of celestial dynamics. The distribution of matter in the disk determines the types of planets that form. Closer to the star, where temperatures are higher, only rocky materials can survive, leading to the formation of terrestrial planets like Earth and Mars. Farther out, where it's colder, ices and gases dominate, giving rise to gas giants like Jupiter and Saturn. The result is a diverse family of planets, each with its own unique characteristics, yet all bound by the same gravitational forces. Gravity doesn't just shape the planets, it also influences their orbits. As planets form, they interact with the remaining material in the disk, gradually clearing their paths and settling into stable orbits. This process, known as orbital migration, can cause planets to move closer to or farther from their star, shaping the final architecture of the solar system. It's a delicate dance where gravity and motion work together to create a harmonious system. The birth of a solar system is a testament to gravity's power as both a creator and an organizer. From the collapse of a molecular cloud to the formation of planets and the stabilization of orbits, gravity is the invisible hand guiding every step. And as we study other solar systems throughout the galaxy, we see the same processes at work, reminding us that the universe operates by universal rules. Each solar system is a unique masterpiece, yet all are born from the same fundamental principles. By understanding how gravity shapes these systems, we gain insight into our own origins and perhaps even the potential for life elsewhere in the cosmos. The formation of solar systems isn't just a story of creation, it's a window into the forces that shape the universe itself. The discovery of exoplanets, planets orbiting stars beyond our solar system, has opened a new chapter in our exploration of the universe. For centuries, humans could only wonder whether other worlds existed among the stars. Today, thanks to advancements in technology and ingenuity, we know not only that they exist, but that they come in astonishing variety. From scorching, gas giants orbiting close to their stars to icy worlds drifting in the distant reaches of their systems, exoplanets have transformed our understanding of celestial dynamics and the gravitational forces that shape them. So, how do astronomers find these distant worlds? Detecting exoplanets is no small feat. Unlike stars, planets don't emit their own light, making them incredibly difficult to spot directly. Instead, scientists rely on indirect methods, using the subtle effects that planets have on their host stars. One of the most successful techniques is the transit method, where a planet passes in front of its star, causing a tiny dip in the star's brightness. This method, used by missions like NASA Kepler and TESS telescopes, has revealed thousands of exoplanets, from massive, hot Jupiters to rocky, super-Earths. Another technique, called the radial velocity method, detects the wobble of a star caused by the gravitational tug of an orbiting planet. These methods, combined with direct imaging and gravitational microlensing, have painted a vivid picture of the incredible diversity of planetary systems. What makes these discoveries so fascinating is the sheer variety of exoplanets and their orbits. Some planets orbit so close to their stars that a single year lasts just a few Earth days, while others drift in wide, elongated paths that take centuries to complete. These orbits are shaped by the same gravitational forces that govern our solar system, but with twists and surprises. For example, some systems feature eccentric planets with highly elliptical orbits, a stark contrast to the nearly circular paths of planets like Earth. Others have multiple planets locked in resonant orbits, where their gravitational interactions create rhythmic patterns, much like the moons of Jupiter. These findings challenge our assumptions about how planetary systems form and evolve, showing that gravity can create an almost infinite array of configurations. But perhaps the most exciting aspect of exoplanet research is the search for Earth-like worlds, planets that could potentially support life. Astronomers have identified dozens of planets within the habitable zone, the region around a star where temperatures might allow liquid water to exist. Kepler 452b, for instance, is often called Earth's cousin due to its similar size and orbit. While we don't yet know if these worlds have atmospheres or oceans, their discovery fuels the hope that we're not alone in the universe. The search for life beyond Earth is one of the most profound questions in science, and exoplanets are at the heart of this quest. Exoplanets also offer a unique window into the early stages of planetary formation. By studying young stars surrounded by protoplanetary disks, scientists can observe how planets emerge from the swirling gas and dust. These observations reveal how gravity shapes the birth of worlds, pulling material together and carving out gaps in the disks where planets are forming. It's a process that mirrors the early history of our own solar system, helping us piece together the story of how planets like Earth came to be. The study of exoplanets has not only expanded our knowledge of the universe, but also deepened our appreciation for the gravitational forces that govern it. Each new discovery adds another layer to our understanding of celestial dynamics, revealing the intricate interplay of gravity, motion, and time. As we continue to explore these distant worlds, we're not just uncovering the secrets of other planets, we're gaining new insights into the cosmic dance that shapes all of existence. Exoplanets remind us that the universe is a place of endless wonder, filled with worlds waiting to be discovered and stories waiting to be told. While many stars shine alone, like our Sun, a significant number of stars in the universe are locked in a cosmic partnership, orbiting each other in a gravitational embrace. These are binary star systems, pairs of stars bound together by their mutual gravity, dancing around a shared center of mass. This stellar duet is not just a rare sight, it's a window into the intricate ways gravity shapes the cosmos. From their mesmerizing orbits to the dramatic phenomena they create, binary stars offer a unique perspective on the forces that govern the universe. At the heart of every binary system is a delicate balance between gravity and motion. Imagine two stars circling each other, their gravitational pull keeping them in a perpetual dance. The closer the stars are, the faster they move, and the stronger their gravitational bond. Some binary stars orbit so closely that they complete a full circle in just a few days, while others take centuries to complete a single lap. These orbits aren't just random. They're shaped by the masses of the stars and the distances between them, following the same laws of celestial dynamics that govern planets and moons. One of the most striking features of binary systems is the phenomenon of stellar eclipses. When the stars in a binary system pass in front of each other from our perspective, they create a temporary dip in brightness. These eclipses aren't just beautiful to observe, they're also incredibly useful for astronomers. By measuring the changes in light, scientists can determine the stars' sizes, masses, and even their compositions. It's like peering into the inner workings of a cosmic clock, where every dip and rise reveals new details about the stars' lives. But binary stars aren't just passive dancers. They can also interact in dramatic ways. In some systems, one star may siphon material from its companion, a process known as mass transfer. Imagine a star slowly pulling gas from its neighbor, forming a swirling disk of material that spirals inward. This process can lead to explosive events, such as nova or even supernova, as the stolen material ignites on the surface of the receiving star. In extreme cases, the transfer of mass can alter the star's orbits, creating a dynamic and ever-changing system. Binary stars also play a crucial role in the evolution of galaxies. Many of the massive stars we observe in the universe are part of binary systems, and their interactions can have far-reaching consequences. For instance, when one star in a binary system explodes as a supernova, it can send its companion hurtling through space at incredible speeds, creating what's known as a runaway star. These high-speed stars can travel across entire galaxies, leaving a trail of new star formation in their wake. In this way, binary systems are not just celestial curiosities, they're engines of change, driving the evolution of galaxies over billions of years. The study of binary stars also sheds light on some of the universe's most extreme objects. Many black holes and neutron stars, the dense remnants of massive stars, are found in binary systems. These objects can pull material from their companions, heating it to incredible temperatures and emitting powerful bursts of X-rays. By observing these systems, scientists can learn about the behavior of matter under extreme conditions, offering insights into the nature of gravity, spacetime, and even the limits of physics itself. Binary stars remind us that the universe is a place of endless complexity and beauty. They show us how gravity not only binds objects together, but also shapes their evolution, creating phenomena that range from the subtle to the spectacular. Whether they are eclipsing each other, transferring mass, or hurtling through space, binary stars are a testament to the power of celestial dynamics. And as we continue to study these stellar partnerships, we gain a deeper understanding of the gravitational forces that orchestrate the grand dance of the cosmos. In the vast theater of the cosmos, few events rival the sheer power and spectacle of a supernova, a star's explosive finale. These cosmic fireworks are not just awe-inspiring, they're transformative, reshaping the universe and seeding it with the building blocks of life. But what exactly causes a star to explode, and how does gravity play a role in this cataclysmic event? Let's step into the life cycle of a massive star and uncover the forces behind one of the universe's most dramatic performances. When a star many times more massive than our Sun exhausts its nuclear fuel, it faces a crisis. For millions or even billions of years, the star's core has been a battleground, where the outward pressure of nuclear fusion fights against the inward pull of gravity. But when the fuel runs out, gravity gains the upper hand. The core collapses under its own weight, squeezing matter into an incredibly dense state. This sudden collapse releases an unimaginable amount of energy, triggering a shockwave that rips through the star's outer layers. The result is a supernova, a burst of light so intense that it can outshine an entire galaxy. Supernovae are not just about destruction, they're also about creation. In the fiery chaos of the explosion, temperatures and pressures soar to levels that forge new elements. Elements like iron, gold, and uranium, which are essential to life and technology, are born in the heart of these stellar explosions. As the shockwave expands, it scatters these heavy elements across space, enriching the surrounding gas and dust. Over time, this material becomes the raw ingredient for new stars, planets, and even living beings. In a very real sense, we are all made of stardust, forged in the crucible of supernova. But the impact of a supernova doesn't stop there. The explosion sends shockwaves rippling through the surrounding interstellar medium, compressing gas and triggering the formation of new stars. These shockwaves can also disrupt nearby star systems, altering their orbits or even ejecting planets into the void. In this way, supernovae act as cosmic sculptors, shaping the structure of galaxies and influencing the birth and evolution of future generations of stars. Supernovae also leave behind remarkable remnants. Sometimes, the core of the star survives the explosion, collapsing into a neutron star, a city-sized object so dense that a teaspoon of its material would weigh billions of tons. In the most extreme cases, the core collapses into a black hole, a region of spacetime where gravity is so intense that not even light can escape. These remnants continue to influence their surroundings, emitting powerful radiation and sometimes even forming binary systems with other stars. The study of supernovae is not just about understanding the end of stars, it's about uncovering the forces that shape the universe. From the creation of heavy elements to the birth of new stars and the formation of black holes, supernovae are a testament to the power of gravity and the interconnectedness of the cosmos. They remind us that even in destruction, there is creation, and that the universe is a dynamic, ever-changing place. As we continue to observe these spectacular events, we gain new insights into the forces that govern the universe and our place within it. Supernovae are not just the end of a star's story, they are the beginning of countless others. When a massive star reaches the end of its life and explodes in a supernova, it doesn't always vanish completely. Sometimes, the core of the star survives, collapsing under the crushing force of gravity into one of the most extreme objects in the universe, a neutron star. Imagine squeezing the mass of our Sun, a sphere nearly 1.4 million kilometers across, into a city-sized object just 20 kilometers wide. The result is a neutron star, a cosmic oddity so dense that a single sugar cube-sized piece would weigh billions of tons. These objects are not just remnants of stellar death, they're laboratories where gravity pushes the boundaries of physics. Neutron stars are born in the fiery aftermath of a supernova, when the star's core collapses under its own immense gravity. Protons and electrons are forced together, merging into neutrons and creating a super-dense material unlike anything found on Earth. This process doesn't just compress matter, it also generates a magnetic field trillions of times stronger than Earth's. Some neutron stars spin rapidly, emitting beams of radiation that sweep across the cosmos like cosmic lighthouses. These spinning neutron stars are known as pulsars, and their rhythmic pulses of light and radio waves have made them invaluable tools for astronomers. Pulsars are nature's precision clocks, rotating with such stability that their pulses can be predicted to within a fraction of a second. This makes them ideal for testing the laws of physics in extreme conditions. For instance, the first indirect evidence of gravitational waves came from observing a pulsar in a binary system. As the pulsar and its companion orbited each other, their gravitational interaction caused them to spiral closer together, losing energy in the form of ripples in spacetime. This discovery, made in the 1970s, confirmed a key prediction of Einstein's theory of general relativity and earned its discoverers the Nobel Prize in Physics decades later. But neutron stars aren't just stellar timekeepers, they're also cosmic powerhouses. When two neutron stars orbit each other, their immense gravity creates ripples in spacetime, known as gravitational waves. In 2017, scientists made history by detecting these waves for the first time, along with the accompanying light from the collision of two neutron stars. This event, called a kilonova, was a dazzling display of cosmic fireworks, producing gold, platinum, and other heavy elements in a matter of seconds. It was a vivid reminder that neutron stars are not just remnants of the past, they're creators of the future, seeding the universe with the materials needed for planets and life. The study of neutron stars and pulsars also offers insights into the nature of matter itself. At their cores, the pressure is so intense that protons and neutrons may break down into a soup of quarks, the fundamental building blocks of matter. This quark-gluon plasma is a state of matter that hasn't existed since the earliest moments of the universe, making neutron stars a window into the physics of the Big Bang. By observing these objects, scientists can explore questions about the fundamental forces of nature and the limits of what matter can endure. Neutron stars and pulsars are more than just gravity's extreme laboratories, they're reminders of the universe's capacity for both beauty and violence. From their precise pulses to their cataclysmic collisions, these objects reveal the intricate interplay of gravity, motion, and time. They challenge us to rethink our understanding of the cosmos and inspire us to explore the universe's deepest mysteries. As we continue to study these stellar remnants, we're not just uncovering the secrets of neutron stars, we're gaining a deeper appreciation for the forces that shape the universe and our place within it. In the vast expanse of the universe, gravity doesn't just pull objects together, it also creates ripples that travel across the fabric of spacetime itself. These ripples, known as gravitational waves, are like cosmic echoes, carrying information about some of the most violent and energetic events in the cosmos. Imagine tossing a stone into a still pond and watching the ripples spread outward. Gravitational waves are similar, but instead of water, they ripple through the very fabric of reality, created by massive objects like black holes or neutron stars accelerating through space. The story of gravitational waves begins with Albert Einstein. In 1916, as part of his theory of general relativity, Einstein predicted that massive objects could distort spacetime, creating waves that propagate outward at the speed of light. But for decades, these waves remained theoretical, too faint to detect with the technology of the time. It wasn't until the 21st century that scientists finally captured the first direct evidence of gravitational waves, a discovery that would change the way we observe the universe. The breakthrough came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the unmistakable signature of two black holes colliding over 1.3 billion light-years away. The signal was incredibly faint, a tiny wobble in spacetime lasting just a fraction of a second, but it was enough to confirm Einstein's century-old prediction and open a new window into the cosmos. Since then, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events, from black hole mergers to neutron star collisions. So, how do gravitational waves form? When massive objects like black holes or neutron stars orbit each other, their immense gravity creates distortions in spacetime. As they spiral closer together, these distortions intensify, sending ripples outward like waves on a pond. The faster the objects move and the more massive they are, the stronger the waves. When they finally collide, the resulting burst of energy sends a powerful gravitational wave surging through the universe, carrying with it a wealth of information about the event that created it. But detecting these waves is no easy task. Gravitational waves stretch and compress spacetime as they pass, but the effect is incredibly small, far smaller than the width of an atom. To measure such tiny changes, LIGO uses lasers split into two perpendicular beams, each traveling down a 4-kilometer-long tunnel. When a gravitational wave passes through, it alters the length of one tunnel slightly compared to the other, creating an interference pattern in the laser light. This delicate setup, combined with cutting-edge technology, allows scientists to detect ripples in spacetime from billions of light-years away. What makes gravitational waves so exciting is what they reveal about the universe. Unlike light, which can be absorbed or blocked by dust and gas, gravitational waves travel unimpeded, offering a clear view of events that would otherwise remain hidden. They've allowed us to hear the collision of black holes, witness the explosive merger of neutron stars, and even test the limits of Einstein's theory of gravity. Each detection adds a new piece to the puzzle, helping us understand the forces that shape the cosmos. Gravitational waves also provide a unique way to study the universe's most extreme objects. For example, when LIGO detected the collision of two neutron stars in 2017, it wasn't just a triumph of technology, it was a scientific goldmine. The event, known as a kilonova, produced both gravitational waves and a burst of light, allowing astronomers to observe it across multiple wavelengths. This rare combination of data revealed the origins of heavy elements like gold and platinum, showing how neutron star collisions enrich the universe with the building blocks of planets and life. The discovery of gravitational waves has transformed our understanding of the universe, giving us a new way to explore the gravitational ballet of the cosmos. They remind us that the universe is not just a static collection of stars and planets, it's a dynamic, ever-changing place, filled with events that ripple across space-time and shape the fabric of reality. As we continue to detect and study these waves, we're not just observing the universe, we're listening to it, uncovering the hidden rhythms that govern the dance of gravity and time. The universe isn't a random scattering of galaxies, it's a meticulously woven tapestry, a cosmic web where galaxies, clusters, and vast voids are interconnected by invisible threads of dark matter. This intricate structure, stretching across billions of light-years, is gravity's masterpiece on the grandest scale. But how does this web form, and what role does gravity play in shaping its immense design? To understand this, we need to step back in time, to the very beginnings of the universe. In the early universe, just moments after the Big Bang, the cosmos was a nearly uniform sea of particles and energy. But even then, tiny fluctuations in density began to emerge, like ripples on the surface of a calm pond. These fluctuations, though minuscule, were the seeds of the cosmic web. Gravity, the great sculptor of the universe, began to amplify these differences. Over billions of years, regions with slightly more matter pulled in more material, growing denser and denser, while less dense regions became emptier. This process, driven by gravity, created a vast network of filaments, nodes, and voids, forming the backbone of the cosmic web. At the intersections of these filaments lie galaxy clusters, the universe's largest gravitationally bound structures. These clusters are like bustling cities in the cosmic web, home to hundreds or even thousands of galaxies. Gravity's pull doesn't just hold these clusters together, it also shapes their evolution. As galaxies within clusters move and interact, they can collide, merge, and trigger bursts of star formation. These interactions are a testament to gravity's enduring influence, not just in holding the universe together, but in driving its constant transformation. But the cosmic web isn't just about the clusters, it's also about the filaments that connect them. These filaments, made up of dark matter and gas, act as cosmic highways, guiding the flow of matter across the universe. Along these filaments, galaxies and gas clouds are funneled toward the clusters, feeding their growth and shaping their structure. It's a dynamic process where gravity acts as both architect and conductor, guiding the movement of matter on scales we can barely comprehend. One of the most striking features of the cosmic web is the presence of voids, vast, nearly empty regions that stretch between the filaments. These voids aren't just empty space, they're an essential part of the web's structure. Gravity's influence is weaker here, allowing galaxies and clusters to form along the edges of these voids, like islands in a cosmic sea. The interplay between the dense filaments and the empty voids creates a delicate balance, a cosmic dance where gravity's pull shapes the universe's large-scale structure. The cosmic web isn't just a static structure, it's a dynamic, evolving system. Over billions of years, gravity continues to shape and reshape the web, pulling matter into denser regions and expanding the voids. This ongoing process is driven by dark matter, the invisible scaffolding that holds the web together. Without dark matter's gravitational influence, the cosmic web, as we know it, wouldn't exist. Its presence is a reminder that much of the universe's structure is shaped by forces we can't see, but can observe through their effects. Understanding the cosmic web isn't just about mapping the universe, it's about uncovering the fundamental forces that govern it. By studying the distribution of galaxies and the flow of matter along the filaments, scientists can trace the history of the universe and predict its future. The cosmic web is a testament to gravity's power, a reminder that even on the largest scales, the universe is governed by the same forces that shape our everyday lives. It's a story of connection, evolution, and the enduring influence of gravity, weaving the fabric of the cosmos into a grand, interconnected whole. Galaxy collisions are the universe's ultimate cosmic showdowns, where immense gravitational forces pull entire galaxies together in a breathtaking dance of destruction and creation. Picture two galaxies, each containing billions of stars, hurtling toward each other at incredible speeds. Yet, despite their size and mass, the likelihood of stars actually colliding is surprisingly low. Why? Because space is vast, and stars are tiny compared to the distances between them. Instead, it's the gravitational forces between these galaxies that dominate, bending their shapes, igniting bursts of star formation, and reshaping their futures in profound ways. When galaxies collide, their gravitational fields interact in a complex and mesmerizing way. As they draw closer, tidal forces created by the pull of gravity stretch and distort their structures. Long, tidal tails of gas, dust, and stars can be flung outward, forming delicate arcs and streams that stretch across the cosmos. These tails are like cosmic brushstrokes, painting a vivid picture of the forces at work. Inside the galaxies, the immense gravitational interactions compress clouds of gas, triggering the birth of new stars. These starburst regions shine brightly, illuminating the chaos of the collision with brilliant clusters of young, hot stars. One of the most fascinating outcomes of galaxy collisions is the formation of elliptical galaxies. Unlike the iconic spirals with their swirling arms, elliptical galaxies are smooth, featureless, and shaped like footballs. Many of these galaxies are thought to be the result of massive collisions between spiral galaxies. When two spirals merge, their stars and gas are thrown into chaotic orbits, eventually settling into a more spherical shape. The collision also heats up the gas, preventing it from forming new stars, which is why elliptical galaxies are often filled with older, redder stars. These galactic mergers are a key part of the universe's evolution, transforming young, star-forming spirals into mature, quiet ellipticals. But galaxy collisions aren't just about destruction, they're also about renewal. The intense gravitational forces can funnel gas into the centers of galaxies, feeding supermassive black holes and igniting some of the most energetic phenomena in the universe: active galactic nuclei. These blazing cores can outshine entire galaxies, emitting vast amounts of energy across the electromagnetic spectrum. In this way, galaxy collisions don't just reshape galaxies, they power some of the universe's most dramatic events. The Milky Way itself is no stranger to galactic collisions. In fact, our galaxy is on a collision course with the Andromeda Galaxy, our nearest galactic neighbor. Billions of years from now, these two spirals will merge, creating a new, larger galaxy that astronomers have nicknamed Milkdromeda. While this event won't happen for another 4 to 5 billion years, it's a reminder that the universe is constantly evolving, driven by the relentless pull of gravity. Galaxy collisions also play a crucial role in the large-scale structure of the universe. As galaxies merge and grow, they form the building blocks of galaxy clusters and superclusters, the largest structures in the cosmos. These collisions are part of a grand cycle, where gravity shapes the universe from the smallest scales to the largest. Each collision is a cosmic story, a moment in the ongoing narrative of the universe's evolution. By studying galaxy collisions, we gain a deeper understanding of how gravity shapes the cosmos. These events are not just spectacular to observe, they are fundamental to the way the universe works. From the birth of new stars to the formation of elliptical galaxies and the feeding of supermassive black holes, galaxy collisions are a testament to the power and beauty of celestial dynamics. They remind us that the universe is not a static place but a dynamic, ever-changing stage where gravity is the unseen force driving the action. Gravity has shaped the universe from its earliest moments, but its influence extends far beyond the present. It will also determine the ultimate fate of everything we know. As we peer into the distant future, the interplay between gravity and the mysterious force of dark energy holds the key to understanding how the cosmos will end. Will the universe collapse in on itself, expand forever, or meet some other dramatic conclusion? The answers lie in a delicate cosmic balance, where the forces of attraction and repulsion dictate the destiny of galaxies, stars, and even spacetime itself. One possible fate for the universe is the Big Crunch, a scenario where gravity ultimately overpowers the expansion driven by dark energy. In this scenario, the universe would slow its expansion, stop, and then begin to contract. Galaxies would draw closer together, temperatures would rise, and eventually, all matter and energy would collapse into an unfathomably dense point, a cosmic mirror of the Big Bang. This dramatic end would be the ultimate triumph of gravity, pulling everything back to a singularity. While the Big Crunch was once a leading theory, modern observations suggest it's less likely, as the universe's expansion appears to be accelerating, not slowing down. On the other end of the spectrum lies the Big Freeze, also known as heat death. This scenario occurs if dark energy continues to dominate, pushing the universe into an ever-accelerating expansion. Over trillions of years, galaxies would drift apart, stars would burn out, and the universe would grow colder and darker. Eventually, even black holes would evaporate, leaving behind a vast, empty expanse of space where nothing happens, a state of maximum entropy. This bleak outcome paints a picture of a universe where gravity's pull is no match for the relentless push of dark energy, but these aren't the only possibilities. Some theories suggest a more dramatic end, the Big Rip. In this scenario, dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a collapse or a fade, but with a violent, all-encompassing rupture. While this might sound like science fiction, it's a real possibility if dark energy behaves in unexpected ways, overwhelming even the strongest gravitational bonds. The fate of the universe isn't just a question of gravity versus dark energy, it's also about the universe's geometry. If the universe is flat, as current observations suggest, it will continue to expand forever, leading to the Big Freeze. If it's curved, it could eventually collapse into a Big Crunch, and if dark energy evolves over time, it could trigger entirely new scenarios we haven't yet imagined. Each possibility hinges on the delicate balance between gravity's pull and the repulsive force of dark energy, a cosmic tug-of-war that will play out over eons. What makes these questions so profound is that they're not just about the universe's end, they are about its beginning and its present. By studying the expansion of the universe, the distribution of galaxies, and the behavior of dark energy, scientists are piecing together the story of how gravity shapes the cosmos. Every observation, from the light of distant supernovae to the echoes of gravitational waves, brings us closer to understanding the universe's ultimate destiny. The fate of the universe is more than a scientific puzzle. It's a reminder of our place in the cosmos. It challenges us to think beyond our lifetimes, beyond even the lifespan of stars and galaxies, and to consider the grand, sweeping narrative of existence. As we continue to explore the universe, from the tiniest particles to the largest structures, we're not just uncovering the secrets of gravity and dark energy, we're uncovering the story of everything. And in that story, we find a universe that's not just expanding, but also evolving, filled with endless possibilities and mysteries waiting to be unraveled. Gravity isn't just the force that binds galaxies and shapes the orbits of planets. It's also a silent architect of life itself. From the formation of habitable worlds to the delicate balance of conditions needed for life to thrive, gravity plays a pivotal role in the story of astrobiology, the study of life beyond Earth. But how does this invisible force influence the potential for life in the universe? To answer that, we need to look at the cosmic environments where life might emerge and the ways gravity shapes them. One of the most critical concepts in astrobiology is the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right. Gravity is at the heart of this balance. A planet's distance from its star determines how much heat it receives, but gravity also plays a role in maintaining a stable atmosphere. Without sufficient gravity, a planet's atmosphere could escape into space, leaving it barren and unable to retain water or heat. On the other hand, a planet with too much gravity might trap too much atmosphere, creating crushing pressures and runaway greenhouse effects. The Goldilocks zone isn't just about location, it's about gravity's ability to create and sustain the right conditions for life. But gravity's influence doesn't stop at atmosphere and temperature. It also shapes the very structure of planets. Take Earth, for example. Our planet's gravity, combined with its molten core, generates a magnetic field that shields us from harmful solar radiation. This protective barrier is essential for life as we know it, allowing organisms to thrive on the surface without being bombarded by deadly cosmic rays. Without gravity's role in creating this magnetic shield, life on Earth might never have evolved beyond its simplest forms. Tidal forces, another product of gravity, also play a surprising role in the potential for life. When a planet or moon orbits close to a larger body, like a star or gas giant, the gravitational tug creates tidal heating. This process can generate enough internal heat to keep subsurface oceans liquid, even in frigid outer regions of a solar system. Europa, one of Jupiter's moons, is a prime example. Beneath its icy crust lies a vast ocean, kept warm by the constant flexing caused by Jupiter's gravity. This tidal heating makes Europa one of the most promising places to search for extraterrestrial life in our own solar system. Gravity, in this case, isn't just a force, it's a source of energy, a cosmic engine that could power life in the most unexpected places. Gravity also influences the evolution of life itself. On Earth, gravity has shaped the way organisms move, grow, and interact with their environment. From the way plants grow upward against gravity's pull to the way animals have evolved skeletons to support their weight, gravity has been a constant, invisible force guiding the development of life. Even the simplest organisms are shaped by gravity, whether it's bacteria moving in response to gravitational cues or the way gravity affects the circulation of fluids in living systems. Astrobiology offers a unique perspective on gravity's role in the universe. It's not just about the formation of stars and galaxies, it's about the conditions that make life possible. By studying how gravity shapes habitable planets, drives tidal forces, and influences the evolution of life, we gain a deeper appreciation for the delicate balance that allows life to exist. Whether we're looking at the Goldilocks zone, the magnetic fields of Earth, or the subsurface oceans of Europa, gravity is the unseen force that connects the cosmos to the potential for life. And as we search for life beyond Earth, we're reminded that gravity isn't just a force, it's a storyteller, weaving the narrative of life into the fabric of the universe. Tidal forces are gravity's quiet yet powerful signature, shaping the cosmos in ways that often go unnoticed. These forces arise when one celestial body's gravity pulls differently on various parts of another object, creating a stretching and squeezing effect. This subtle but profound influence can be seen everywhere, from the rhythmic rise and fall of ocean tides on Earth to the dramatic volcanic eruptions on distant moons. It's gravity's way of leaving its mark, not just through massive collisions or explosive events, but through a constant, delicate tug that molds the universe over time. On Earth, the most familiar example of tidal forces is, of course, our ocean tides. the Moon's gravity pulls more strongly on the side of Earth closest to it, creating a bulge in the ocean. At the same time, the opposite side of Earth experiences a lesser pull, forming a second bulge. As Earth rotates, these bulges move, causing the tides to rise and fall. But tides aren't just about water, they also affect the solid ground beneath our feet, though to a much smaller degree. Even the Earth's crust rises and falls slightly in response to the Moon's gravitational pull, a phenomenon known as Earth tides. Tidal forces don't just shape Earth, they also play a crucial role in the evolution of moons and planets. Take Jupiter's moon Io, for example. This small, rocky world is the most volcanically active object in the solar system, and it's all thanks to gravity. Io orbits so close to Jupiter that the planet's immense gravitational pull creates intense tidal heating. The constant stretching and squeezing of Io's interior generates enough heat to melt rock, powering its spectacular volcanic eruptions. It's a vivid example of how tidal forces can transform a seemingly inert world into a dynamic, fiery landscape. But tidal forces don't always lead to chaos. They can also create stability. Consider the relationship between Earth and the Moon. Over billions of years, tidal forces have slowed Earth's rotation, gradually lengthening our days. At the same time, the Moon has been moving farther away from Earth, a process known as tidal acceleration. This delicate dance between gravity and motion has shaped the history of both bodies, leaving them locked in a gravitational embrace that continues to evolve. Tidal forces also play a role in the life cycles of stars. When two stars orbit each other closely, their mutual gravitational pull can create tidal distortions, stretching each star into an egg-like shape. In extreme cases, this can lead to mass transfer, where one star siphons material from its companion. This process can trigger dramatic events, such as nova or even supernova, reshaping the stars and their surroundings. It's a reminder that tidal forces aren't limited to planets and moons, they're a universal phenomenon, influencing objects across the cosmos. Even on the largest scales, tidal forces leave their mark. When galaxies collide, the immense gravitational interactions can stretch and distort their shapes, creating tidal tails of stars and gas that stretch across millions of light years. These interactions don't just reshape the galaxies, they also trigger bursts of star formation, seeding the universe with new generations of stars. In this way, tidal forces are not just a local effect, they're a fundamental part of the cosmic dance, shaping the universe on every scale. From the tides that shape our oceans to the volcanic fury of distant moons, tidal forces are a testament to gravity's subtle yet profound influence. They remind us that even the smallest tugs can have far-reaching consequences, sculpting the cosmos in ways that are both beautiful and awe-inspiring. As we continue to explore the universe, from the moons of Jupiter to the collisions of galaxies, we're constantly reminded of the intricate ways gravity shapes the world around us. Tidal forces are more than just a curiosity, they're a window into the delicate balance that governs the cosmos, a balance that continues to unfold with every passing moment. Out in the vast expanse of space, there are special places where gravity performs a delicate balancing act, regions known as Lagrange points. Named after the 18th century mathematician Joseph Louis Lagrange, these points are positions where the gravitational pull of two large bodies, like a star and a planet, perfectly balances the centripetal force needed for a smaller object to move with them. It's as if gravity itself has carved out pockets of stability in the chaos of space, offering unique opportunities for exploration and observation. There are 5 Lagrange points associated with any two-body system, labeled L1 through L5. The most well-known of these, L1 and L2, are located along the line connecting the two larger bodies. L1, for example, sits between Earth and the Sun, offering an unobstructed view of our star. This makes it an ideal location for solar observatories like NAS, a Solar and Heliospheric Observatory, or SOHO, which monitors the Sun's activity and provides early warnings of solar storms. L2, on the other hand, lies just beyond Earth's shadow, making it perfect for telescopes like the James Webb Space Telescope, which can peer deep into the cosmos without interference from Earth's light or heat. But Lagrange points aren't just about observation, they are also about stability. Objects placed at these points can remain in a relatively fixed position with minimal fuel consumption, making them invaluable for long-term missions. For instance, the L2 point has become a hub for astronomical research, hosting missions that study everything from the cosmic microwave background to the formation of distant galaxies. It's a testament to how gravity's subtle interplay can create opportunities for discovery that would otherwise be impossible. The L3, L4, and L5 points, while less commonly used, are no less fascinating. L4 and L5, in particular, form an equilateral triangle with the two larger bodies and are inherently stable. These points are like cosmic parking spots, where objects can remain indefinitely without drifting away. In fact, L4 and L5 are often home to natural collections of space debris, such as the Trojan asteroids that orbit the Sun alongside Jupiter. These regions are a reminder that Lagrange points aren't just human-made conveniences, they're natural features of the gravitational landscape. Lagrange points also hold exciting potential for future missions. Scientists have proposed using L1 as a staging ground for missions to the Moon or Mars, where spacecraft could refuel or transfer cargo with minimal energy expenditure. Others have envisioned using L5 as a base for asteroid mining, taking advantage of its stability to process resources from nearby space rocks. These ideas may sound like science fiction, but they're grounded in the very real physics of gravity and motion. Beyond their practical applications, Lagrange points offer a deeper insight into the gravitational ballet of the cosmos. They reveal how the universe operates not just through brute force, but through delicate equilibriums, where the push and pull of gravity create pockets of order in the vastness of space. By studying these points, we not only advance our exploration of the universe, but also deepen our understanding of the forces that shape it. Lagrange points are a reminder that even in the seemingly chaotic dance of celestial bodies, there are moments of perfect balance. They're a testament to the elegance of gravity, a force that not only binds the universe together, but also carves out spaces for discovery and wonder. As we continue to explore these gravitational sweet spots, we uncover not just new opportunities for science, but also new ways to connect with the cosmos. Picture a planet drifting alone through the cold, dark void of space, no star to warm it, no solar system to call home. This isn't science fiction, it's the reality of rogue planets, celestial nomads that have been flung from their star systems and now wander the cosmos. These lonely worlds are gravity's wanderers, shaped by the same forces that govern the orbits of planets and the collisions of galaxies. But how do they come to be, and what secrets do they hold about the universe? Rogue planets begin their lives like any other planet, forming within the swirling disks of gas and dust around young stars. But sometimes, during the chaotic early days of a star system, gravitational interactions can fling a planet out into the void. Imagine a game of cosmic pinball, where a close encounter with a massive planet or a passing star sends a smaller world hurtling into interstellar space. Once ejected, these planets are no longer bound by the gravity of a star, left to drift endlessly through the galaxy. The journey of a rogue planet is one of solitude and extremes. Without a star to provide warmth, these planets are frozen and dark, their surfaces shrouded in perpetual night. Yet, some may still harbor the potential for life. Scientists speculate that rogue planets could maintain subsurface oceans, heated by the decay of radioactive elements or the gravitational pull of a moon. These hidden oceans, insulated by thick layers of ice, could provide a haven for microbial life, even in the absence of sunlight. It's a tantalizing possibility, a reminder that life might find a way in even the most unexpected corners of the universe. Gravity plays a dual role in the story of rogue planets. On one hand, it's the force that ejects them from their star systems, casting them adrift. On the other, it's the force that shapes their journey through the cosmos. As they drift, rogue planets can be captured by the gravity of passing stars or star clusters, becoming part of a new system. In rare cases, they might even collide with other planets or stars, creating cataclysmic events that reshape entire systems. These interactions are a testament to gravity's enduring influence, even on the fringes of the galaxy. But rogue planets aren't just cosmic oddities, they're also valuable tools for understanding the universe. Because they don't emit light, detecting these worlds is incredibly challenging. Astronomers rely on a technique called gravitational microlensing, where the gravity of a rogue planet bends and magnifies the light of a distant star, creating a temporary brightening. These fleeting events provide a glimpse into the population of rogue planets, revealing that there may be billions of them in our galaxy alone. The existence of rogue planets challenges our understanding of planetary systems and the forces that shape them. They remind us that the universe is far more dynamic and unpredictable than we often imagine. From their violent births to their solitary journeys, these worlds are a testament to gravity's power to create, destroy, and reshape the cosmos. And as we continue to explore the mysteries of rogue planets, we're not just learning about these lonely wanderers, we're uncovering the deeper truths about how gravity orchestrates the universe's grandest performances. Rogue planets are more than just gravity's castaways. They're a window into the chaos and creativity of the cosmos. Whether they're drifting silently through the void or harboring hidden oceans, these worlds challenge us to rethink what it means to be a planet. And as we peer into the darkness, searching for these elusive wanderers, we're reminded that the universe is full of surprises, waiting to be discovered. Beyond the familiar orbits of planets lies a realm of icy wanderers, where the sun's gravity stretches its influence to the very edges of the solar system. This is the domain of the Kuiper Belt and the Oort Cloud, two vast regions filled with frozen remnants from the birth of our cosmic neighborhood. These distant zones are more than just repositories of ancient ice and rock. They're dynamic frontiers where gravity's long arm shapes the fate of countless objects, from tiny comets to dwarf planets like Pluto. The Kuiper Belt, a donut-shaped region extending beyond Neptune, is home to thousands of icy bodies, including dwarf planets and comets. It's often described as a colder, more distant cousin to the asteroid belt, but its composition and history are starkly different. While the asteroid belt is primarily rocky, the Kuiper Belt is a frozen archive, preserving material from the solar system's earliest days. Gravity plays a key role here, not just in keeping these objects in orbit, but in sculpting their paths and interactions. For example, Neptune's gravity has a profound influence on the Kuiper Belt. nudging objects into resonant orbits or even flinging them into the inner solar system as short-period comets. Venturing even farther out, we encounter the Oort cloud, a vast, spherical shell of icy debris that envelops the solar system like a cosmic halo. Unlike the Kuiper belt, which lies within the plane of the solar system, the Oort cloud stretches in all directions, reaching up to 100,000 times the distance from the Earth to the Sun. This distant region is thought to be the source of long-period comets, those rare, spectacular visitors that streak across our skies after spending eons in the deep freeze. The Oort cloud's existence is inferred rather than directly observed, a testament to gravity's ability to hold sway over even the most remote corners of space. The formation of these regions tells a fascinating story about the solar system's infancy. As the planets formed and migrated to their current positions, their gravitational forces scattered countless icy bodies outward. Some were captured in the Kuiper belt, while others were flung even farther, settling in the Oort cloud. This scattering wasn't just a random event, it was a gravitational choreography, with the sun and planets acting as cosmic dancers, shaping the distribution of these icy remnants over billions of years. Comets, those dazzling celestial travelers, are perhaps the most famous products of these distant realms. When a comet is nudged out of the Kuiper belt or Oort cloud by a gravitational disturbance, it begins a long journey toward the sun. As it approaches, the sun's heat vaporizes its icy surface, creating the glowing coma and tail that make comets so captivating. These visitors from the outer solar system are more than just beautiful spectacles, they're time capsules, carrying pristine material from the early solar system that can teach us about its origins. The Kuiper belt and Oort cloud are also treasure troves for discovery. Recent missions like NASA's A New Horizons have revealed stunning details about objects like Pluto and Arrokoth, a Kuiper belt object that looks like two pancakes stuck together. These missions not only expand our knowledge of these distant regions, but also hint at the potential for finding even more exotic objects. Could there be undiscovered dwarf planets, or even evidence of ancient interactions with passing stars? The possibilities are as vast as the regions themselves. Exploring these outer reaches isn't just about cataloging icy bodies. It's about understanding the gravitational forces that have shaped the solar system from its birth to the present day. The Kuiper belt and Oort cloud are more than just distant collections of ice. They're key players in the gravitational ballet, influencing the orbits of comets, the history of planets, and the very structure of our cosmic neighborhood. As we continue to probe these icy frontiers, we're not just uncovering the secrets of the outer solar system, we're piecing together the story of how gravity weaves the fabric of the cosmos. Comets and asteroids are more than just space rocks and icy wanderers, they're time capsules from the early solar system, carrying clues about the universe's origins. These celestial fragments, shaped by gravity over billions of years, tell a story of chaos, creation, and the enduring influence of cosmic forces. From their formation in the swirling chaos of the young solar system to their dramatic encounters with planets today, comets and asteroids are gravity's messengers, offering us a glimpse into the past while reminding us of the dynamic nature of our cosmic neighborhood. Comets with their glowing tails and icy cores are often called dirty snowballs for good reason. They originate in the Kuiper belt and Oort cloud, regions filled with frozen debris left over from the solar system's formation. When a comet is nudged out of its distant orbit by a gravitational disturbance, perhaps from a passing star or the pull of a giant planet, it begins its journey toward the sun. As it approaches, the sun's heat vaporizes its icy surface, creating the spectacular coma and tail that light up our night skies. These tails, which always point away from the sun due to the solar wind, are a vivid reminder of the sun's influence, even on objects billions of miles away. Asteroids, on the other hand, are rocky remnants that mostly reside in the asteroid belt between Mars and Jupiter. Unlike comets, they lack the volatile ices that create glowing tails, but they're no less fascinating. These ancient rocks are thought to be the building blocks of planets that never fully formed, preserved in a gravitational tug-of-war between Jupiter and the Sun. Jupiter's immense gravity prevents these objects from coalescing into a planet, scattering them into the asteroid belt instead. Yet, even here, gravity continues to shape their orbits, occasionally sending them on collision courses with planets including Earth. The role of gravity in the orbits of comets and asteroids is a key part of their story. Comets follow highly elliptical paths, spending most of their time in the frigid outer solar system before swooping in close to the Sun in a dazzling display. Asteroids, meanwhile, have more stable orbits, but they're not immune to gravitational nudges. Over time, interactions with planets can alter their trajectories, sending them into the inner solar system or even causing them to collide with other bodies. These gravitational interactions are a reminder that the solar system is a dynamic, ever-changing place, where even small forces can have dramatic consequences. One of the most dramatic consequences of these interactions is the potential for impacts on Earth. Comets and asteroids have shaped our planet's history in profound ways. The impact of a massive asteroid 66 million years ago is widely believed to have caused the extinction of the dinosaurs, reshaping life on Earth in its aftermath. Smaller impacts, while less catastrophic, still leave their mark, creating craters like Arizona's Meteor Crater and providing scientists with valuable insights into the nature of these objects. Today, astronomers keep a close watch on near-Earth objects, using gravity's laws to predict their paths and assess potential threats. But comets and asteroids aren't just potential hazards, they're also windows into the solar system's past. By studying their composition, scientists can learn about the conditions that existed when the planets formed. Comets, for example, carry water and organic molecules, the building blocks of life, suggesting they may have played a role in delivering these ingredients to Earth. Asteroids, with their varied compositions, offer clues about the diversity of materials that existed in the early solar system. Missions like NASA OSIRIS-REx and ESA's Rosetta have brought back samples from these objects, providing unprecedented insights into their origins. Gravity's role in the lives of comets and asteroids doesn't end with their formation and orbits. It also shapes their interactions with other celestial bodies. When a comet or asteroid passes close to a planet, the planet's gravity can alter its path, sometimes dramatically. This process, known as gravitational perturbation, can send these objects into new orbits, potentially bringing them closer to Earth or flinging them out of the solar system entirely. These interactions are a testament to gravity's far-reaching influence, shaping not just the orbits of planets and moons, but also the paths of these smaller, wandering bodies. Comets and asteroids are more than just remnants of the past, they're active participants in the gravitational ballet of the cosmos. From their formation in the early solar system to their ongoing interactions with planets, these objects remind us that the universe is a place of constant motion and change. By studying them, we gain not only a deeper understanding of the solar system's history, but also a greater appreciation for the forces that continue to shape it. Whether they're lighting up our skies or colliding with planets, comets and asteroids are gravity's messengers, carrying stories of creation, destruction, and the enduring dance of the cosmos. Beyond the planets and stars, hidden in the gravitational embrace of distant worlds, lie moons that orbit planets outside our solar system, exomoons. These elusive celestial bodies, shaped by the gravitational forces of their host planets, are more than just cosmic companions. They're potential havens for life, windows into planetary systems, and key players in the gravitational ballet of the cosmos. But what exactly are exomoons, and how do they form in the first place? Exomoons begin their lives much like the moons in our own solar system, through a combination of gravitational interactions and cosmic collisions. When a young planet forms, it often accumulates a disk of gas and dust around it, similar to the way stars form their planetary systems. Within this disk, smaller bodies can coalesce, eventually becoming moons. Alternatively, a passing object might be captured by the planet's gravity, pulled into orbit, and transformed into a moon. This process, driven by gravity's delicate balance, creates moons that are as diverse as the planets they orbit. One of the most intriguing aspects of exomoons is their potential to host life. Just as moons like Europa and Enceladus in our solar system are thought to harbor subsurface oceans, exomoons could also possess liquid water beneath icy shells. If these moons orbit within their star's habitable zone, the region where temperatures allow liquid water to exist, they could offer conditions ripe for life. Imagine a moon with a thick atmosphere, warmed by tidal forces from its host planet and teeming with microbial organisms. It's a tantalizing possibility that expands our search for life beyond planets to these hidden worlds. Detecting exomoons, however, is no easy task. Unlike planets, which can be spotted through the dimming of a star's light as they pass in front of it, exomoons are much smaller and harder to observe. Scientists rely on subtle gravitational effects, such as the wobble of a planet caused by its moon, or the slight variations in a planet's transit timing. These indirect methods require precise measurements and cutting-edge technology, making the hunt for exomoons one of the most challenging and rewarding pursuits in modern astronomy. Despite the challenges, the search for exomoons has already yielded exciting possibilities. For example, in 2018, astronomers reported the potential discovery of an exomoon orbiting a gas giant in the Kepler 1625 system. While this finding is still debated, it highlights the potential for exomoons to exist in a wide range of planetary systems. Each discovery brings us closer to understanding how common these moons are and what role they play in the evolution of their host planets. Exomoons also offer a unique perspective on the diversity of planetary systems. In our solar system, moons vary dramatically from the volcanic activity of Io to the icy oceans of Europa. Exomoons could be equally diverse, with some orbiting close to their planets and others in distant, stable orbits. Their presence can influence the dynamics of their planetary systems, affecting everything from the planet's rotation to the stability of its orbit. By studying exomoons, we gain insights into the complex interplay of gravity, motion, and time that shapes the cosmos. As we continue to explore the universe, exomoons remind us that the gravitational ballet is far more intricate than we once imagined. These hidden worlds, shaped by the forces of their host planets, challenge us to rethink our understanding of planetary systems and the potential for life beyond Earth. Whether they are icy moons with subsurface oceans or rocky satellites orbiting gas giants, Exomoons are a testament to the endless creativity of the cosmos. And as we uncover their secrets, we're not just discovering new worlds, we're expanding our understanding of gravity's role in the universe's grandest performances. Gravity is often thought of as the force that shapes the paths of planets and galaxies, but its influence extends far beyond space. It also bends time itself. This mind-bending concept, predicted by Albert Einstein's theory of general relativity, reveals that gravity doesn't just pull on objects, it warps the very fabric of spacetime, altering how time flows. The closer you are to a massive object, the slower time moves, a phenomenon known as gravitational time dilation. This isn't science fiction. It's a well-documented effect that has profound implications for our understanding of the universe. Imagine standing near the edge of a black hole, where gravity is so intense that not even light can escape. Here, time would slow to a crawl compared to someone far away in the emptiness of space. A clock ticking seconds near the black hole would appear to run slower to an outside observer. This isn't just a theoretical quirk, it's a measurable effect. For example, satellites in Earth's orbit, where gravity is slightly weaker, experience time ticking faster than clocks on the planet's surface. To keep GPS systems accurate, engineers must account for this difference, adjusting for the fact that time literally moves faster in orbit. Without these corrections, your navigation apps would be off by miles within minutes. But gravitational time dilation isn't just about extreme environments like black holes or high-tech satellites. It's happening right here on Earth, albeit on a much smaller scale. Clocks at sea level, where gravity is stronger, tick ever so slightly slower than those at the top of a mountain. The difference is tiny, just fractions of a second over a lifetime, but it's real. This subtle effect underscores how gravity weaves itself into the very fabric of our daily lives, influencing not just where we are but when we are. The implications of gravitational time dilation stretch far beyond our planet. In the cosmos, massive objects like neutron stars and black holes create dramatic distortions in time. For instance, if you could watch a star orbiting close to a black hole, you'd see its light redshifted and its movement slowed as it neared the event horizon. From the star's perspective, time would pass normally, but to an outside observer, it would appear frozen in time. This bizarre effect isn't just a curiosity, it's a key part of how we understand the behavior of matter and energy in extreme environments. Gravitational time dilation also opens up fascinating questions about the nature of time itself. Is time truly universal, or is it relative, shaped by the gravitational fields we inhabit? Einstein's work suggests the latter, painting a picture of a universe where time is fluid, not fixed. This idea challenges our everyday experience of time as a steady, unchanging force, revealing it instead as a dynamic, malleable dimension intertwined with gravity. It's a reminder that the universe operates on scales and principles far beyond our intuitive understanding. From the synchronization of atomic clocks on Earth to the mind-bending distortions near black holes, gravity's influence on time is a testament to the interconnectedness of space and time. It's a concept that not only deepens our understanding of the cosmos, but also invites us to rethink our place within it. As we continue to explore the mysteries of gravitational time dilation, we're not just uncovering the secrets of the universe, we're gaining a new perspective on the very nature of reality. Gravity, it turns out, isn't just the force that binds the cosmos, it's the force that shapes time itself. Gravity and quantum mechanics, two pillars of modern physics, have each revolutionized our understanding of the universe in their own ways. Gravity, as described by Einstein's general relativity, explains the cosmos on the grandest scales, from the orbits of planets to the bending of light around black holes. Quantum mechanics, on the other hand, delves into the bizarre, counterintuitive world of the very small, governing the behavior of atoms and subatomic particles. Yet, for all their success, these two theories remain fundamentally at odds, creating one of the most profound puzzles in science. How do we reconcile the force that shapes galaxies with the rules that govern the quantum realm? At the heart of this challenge lies a fundamental incompatibility. General relativity describes gravity as the curvature of spacetime, a smooth, continuous fabric shaped by mass and energy. Quantum mechanics, however, operates in a world of probabilities, where particles can exist in multiple states at once, and interactions are governed by discrete packets of energy. These two frameworks work beautifully in their respective domains, but when we try to apply them together, say, to understand the extreme conditions inside a black hole or the first moments of the Big Bang, they clash. The mathematics breaks down, and the universe becomes a paradox. This clash has spurred some of the most ambitious theories in physics, each attempting to bridge the gap between gravity and quantum mechanics. One leading contender is quantum gravity, a framework that seeks to describe gravity in terms of quantum particles. In this view, gravity would be mediated by hypothetical particles called gravitons, much like electromagnetism is carried by photons. But proving the existence of gravitons is no small feat. It would require detecting incredibly subtle interactions, far beyond the reach of current technology. Another approach is string theory, which proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings, existing in multiple dimensions, could unify all forces of nature, including gravity, under a single theoretical umbrella. While string theory offers a tantalizing vision of a unified universe, it remains largely untested, with many of its predictions lying beyond the scope of current experiments. Then there's loop quantum gravity, which suggests that spacetime itself is quantized, composed of tiny, discrete loops. In this model, the fabric of the universe isn't smooth but granular, like a digital image made up of pixels. This idea could potentially resolve the singularities at the heart of black holes, offering a way to understand the universe's most extreme environments without the breakdown of physics. The quest to unite gravity and quantum mechanics isn't just an academic exercise, it's a journey to uncover the deepest truths about the universe. If successful, such a theory could explain the nature of spacetime, the origins of the universe, and even the behavior of black holes. It could also open new doors to technologies we can scarcely imagine, from quantum computers that harness the power of gravity to new forms of energy generation. Yet, for all the progress, the puzzle remains unsolved. The search for a unified theory is a reminder of how much we still have to learn about the cosmos. It's a challenge that pushes the boundaries of human ingenuity, requiring us to rethink our most fundamental assumptions about space, time, and reality itself. As we continue to explore this frontier, we're not just seeking answers, we're redefining the questions. What is the true nature of gravity? How does it interact with the quantum world? And what does this mean for our understanding of the universe's grandest structures? These are the questions that drive physicists today, and they remind us that the universe, for all its mysteries, is a place of endless wonder and possibility. The journey to unite gravity and quantum mechanics is far from over, but with every discovery, we come one step closer to unlocking the secrets of the cosmos. What if our universe is just one among countless others, each governed by its own set of rules and gravitational forces? This is the tantalizing idea behind the multiverse, a concept that stretches the boundaries of our imagination and challenges our understanding of reality. At its core, the multiverse suggests that the cosmos we know is merely a single act in an infinite cosmic play, with parallel universes performing their own gravitational ballets, each with its own unique choreography. One of the key theories supporting the multiverse idea is cosmic inflation. According to this theory, in the earliest moments after the Big Bang, space expanded exponentially faster than the speed of light. This rapid expansion didn't just create our universe, it could have spawned countless others, each bubbling up like separate pockets in a boiling pot. In these other universes, the strength of gravity, the laws of physics, and even the number of dimensions could be radically different. Some might have gravity so weak that stars never form, while others could have gravity so strong that black holes dominate the landscape. The multiverse, in this view, becomes a cosmic laboratory, where gravity takes on infinite forms, shaping universes in ways we can barely comprehend. String theory, another cornerstone of multiverse speculation, takes this idea even further. It proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings of energy. These strings exist in a higher dimensional space, where our familiar 3 dimensions of space and 1 of time are just a small part of a much larger, more complex structure. In this framework, different universes could exist as brains, short for membranes, floating in a higher dimensional space. Gravity, in this scenario, could leak between these brains, creating subtle connections between otherwise isolated universes. It's a mind-bending concept that redefines not just gravity but the very fabric of reality itself. But what does the multiverse mean for celestial dynamics, the gravitational dance that shapes stars, galaxies, and planets? If other universes exist, their gravitational forces could influence the formation and evolution of cosmic structures in ways we can't yet predict. For instance, a universe with stronger gravity might collapse into black holes almost immediately, while one with weaker gravity could stretch endlessly, filled with sparse, dimly lit stars. Our universe, with its finely tuned gravitational constant, seems to strike a delicate balance, allowing for the formation of galaxies, stars, and planets, and ultimately, life. The multiverse theory offers a possible explanation for this balance. If countless universes exist, each with its own set of physical laws, it's statistically inevitable that at least one would have conditions suitable for life. The implications of the multiverse go beyond physics and astronomy. They touch on the very nature of existence. If parallel universes exist, each governed by its own gravitational rules, what does that mean for our place in the cosmos? Are we just one version of reality among an infinite array of possibilities? These questions push the boundaries of science and philosophy, inviting us to rethink not just how the universe works, but why it works the way it does. While the multiverse remains a speculative idea, it's a powerful reminder of gravity's central role in shaping not just our universe, but potentially an infinite number of others. It challenges us to think beyond the confines of our own cosmic neighborhood and imagine a reality where gravity's influence extends across dimensions and universes. As we continue to explore this frontier, we're not just uncovering the secrets of our universe, we're glimpsing the infinite possibilities of existence itself. The multiverse isn't just a theory, it's an invitation to dream, to question, and to explore the gravitational ballet on the grandest stage imaginable. Even with centuries of scientific progress, gravity continues to surprise us. Despite the precise equations of Newton and Einstein, there are still phenomena that defy our current understanding, gravitational anomalies that challenge the very foundation of celestial dynamics. These unexplained quirks in the behavior of objects in space serve as reminders that the universe is far more complex than we might imagine, and that gravity, for all its predictability, still holds secrets waiting to be uncovered. One of the most famous gravitational anomalies is the Pioneer anomaly. In the late 20th century, as NASA Pioneer 10 and 11 spacecraft ventured beyond the solar system, scientists noticed something strange. Both probes were slowing down ever so slightly, as if an unseen force were tugging on them. This unexpected deceleration couldn't be explained by known gravitational forces or even by the tiny push of solar radiation. For decades, the Pioneer anomaly puzzled scientists, sparking theories ranging from errors in measurement to exotic new physics, like the existence of unseen dark matter or even modifications to Einstein's theory of gravity. Eventually, the mystery was attributed to heat radiating unevenly from the spacecraft's power sources, but the case remains a fascinating example of how even small discrepancies can lead to big questions about our understanding of the cosmos. Then there's the flyby anomaly, another head-scratcher for astronomers. When spacecraft like NASA Galileo or the European Space Agency's Rosetta perform gravitational slingshot maneuvers around Earth, they sometimes gain or lose more speed than predicted. These tiny deviations, often just a few millimeters per second, might seem insignificant, but they are enough to suggest that something in our understanding of gravity, or perhaps in the way Earth's gravity interacts with spacecraft, is incomplete. Could there be subtle effects of Earth's rotation or atmosphere that we're missing? Or is there a deeper, more fundamental explanation waiting to be discovered? The flyby anomaly is a reminder that even in well-studied regions of space, surprises can still emerge. Gravitational anomalies like these aren't just scientific curiosities, they are opportunities. Each unexplained phenomenon pushes us to refine our theories, develop new technologies, and question long-held assumptions. For instance, the search for answers to these anomalies has led to advancements in spacecraft design, more precise measurement tools, and even new experiments to test the limits of general relativity. These efforts don't just solve puzzles, they expand our understanding of the universe and the forces that shape it. The implications of gravitational anomalies stretch beyond our solar system. Could similar effects occur in distant star systems or even on galactic scales? If so, they might help explain some of the universe's biggest mysteries, like the nature of dark matter or the acceleration of cosmic expansion. By studying these subtle discrepancies, we're not just solving small puzzles, we're uncovering clues that could reshape our understanding of gravity itself. What makes gravitational anomalies so compelling is their ability to remind us that science is a never-ending journey. Just when we think we've figured everything out, the universe throws us a curveball, challenging us to think deeper and look closer. These anomalies are like cosmic breadcrumbs, leading us toward new discoveries and a deeper appreciation for the complexity of the cosmos. They show us that even in the well-trodden paths of physics, there's always room for wonder, curiosity, and the thrill of the unknown. And as we continue to explore these mysteries, we're not just unraveling the secrets of gravity, we're uncovering the story of the universe itself. Gravity isn't just the force that keeps planets in orbit or galaxies together, it's also a silent guide in our search for extraterrestrial intelligence. From shaping the conditions necessary for life to influencing how we detect cosmic signals, gravity plays a pivotal role in the quest to answer one of humanity's oldest questions: are we alone in the universe? To understand how gravity impacts the search for life, we need to start with the basics: habitable planets. Gravity's pull helps determine whether a planet can hold onto an atmosphere, a crucial ingredient for life as we know it. Too little gravity, and a planet's atmosphere might escape into space, leaving it barren and exposed. Too much gravity, and the atmosphere could become so dense that it traps heat, creating a runaway greenhouse effect. Earth's gravity strikes a delicate balance, allowing for liquid water, moderate temperatures, and the conditions necessary for life to thrive. This balance isn't just luck, it's a product of gravity's precise influence. But gravity's role doesn't stop at creating habitable worlds. It also shapes the evolution of civilizations. Consider how gravity affects the development of technology and exploration. On a high-gravity planet, launching spacecraft would require far more energy, potentially slowing the pace of space exploration. Conversely, on a low-gravity world, building structures or even moving around might be easier, but the lack of a dense atmosphere could pose its own challenges. These factors could influence how or even if a civilization develops the ability to communicate across the stars. When it comes to detecting extraterrestrial intelligence, gravity once again takes center stage. One of the most promising methods for finding alien signals is through gravitational microlensing, a phenomenon where a massive object, like a star or planet, bends and magnifies the light from a more distant object. This technique can reveal planets that might otherwise go unnoticed, including those in the habitable zones of their stars. By studying these microlensing events, scientists can identify potential targets for further observation, bringing us closer to discovering worlds where life, and perhaps intelligence, might exist. Gravity also plays a role in the longevity of civilizations. On a cosmic scale, the stability of a planet's orbit, influenced by gravity, is essential for the long-term survival of life. A planet with a chaotic orbit, constantly swinging between extreme temperatures, would struggle to sustain life over billions of years. Earth's relatively stable orbit, maintained by the gravitational interactions within our solar system, has allowed life to evolve and flourish. This stability isn't just a matter of chance, it's a testament to gravity's ability to create conditions where civilizations can endure and advance. As we continue to search for extraterrestrial intelligence, gravity remains a central theme, guiding our understanding of where and how life might exist. From the formation of habitable planets to the detection of distant signals, gravity's influence is woven into every step of this cosmic quest. And while we may not yet have found definitive proof of intelligent life beyond Earth, gravity reminds us that the universe is vast, complex, and filled with possibilities. Each discovery, each new insight into the role of gravity, brings us closer to answering the profound question of whether we are truly alone, and what that might mean for our place in the cosmos. The gravitational ballet of the cosmos is more than just a force, it's a story, a symphony of motion that has shaped the universe since its very beginning. From the delicate dance of planets around their stars to the explosive collisions of galaxies, gravity is the unseen conductor, orchestrating the movements of celestial bodies with precision and grace. It's a force that binds us to the Earth, connects stars into galaxies, and weaves the fabric of spacetime itself. Yet for all its power, gravity remains one of the universe's greatest mysteries, a force that continues to challenge and inspire us. As we've explored the wonders of celestial dynamics, From the birth of solar systems to the hidden influence of dark matter, one thing has become clear: gravity is far more than just a pull. It's a creator, shaping worlds and igniting stars. It's a destroyer, fueling cataclysmic events that reshape the cosmos. And it's a guide, leading us to new discoveries and deeper questions about the nature of reality. Each observation, each discovery, brings us closer to understanding the intricate dance that defines the universe. But the journey doesn't end here. The cosmos is vast, and there's still so much to uncover. What lies at the heart of a black hole? How does dark energy shape the fate of the universe? Could there be other worlds, hidden in the gravitational embrace of distant stars, waiting to be found? These are the questions that drive us forward, pushing the boundaries of science and imagination. Every discovery is a reminder that the universe is a place of endless wonder, a stage where gravity continues to choreograph the greatest performances in existence. Thank you for joining us on this journey through the gravitational ballet of the cosmos. Your curiosity and support make exploring these mysteries even more rewarding. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments below. Let us know what fascinates you most about gravity and the universe. We'd love to hear from you. Until next time, keep looking up and remember, the cosmos is waiting to reveal its secrets, one gravitational step at a time.